Some buildings have survived for over 1,000 years. They stand firm against earthquakes and fires that flatten modern constructions. This is the power of traditional architecture, a field of ancient wisdom we are just starting to understand. You will learn the hidden principles that allowed structures like Japanese pagodas and medieval castles to endure through centuries of disaster. How did builders without computers create designs that outlast our strongest materials? The answers lie in a forgotten relationship with nature, materials that heal themselves, and shapes that dance with the wind. This knowledge could change how we build everything today. What does it take for a building to truly become eternal? That Roman aqueduct is more than a relic. It is a functioning piece of engineering, a testament to a philosophy of building that thought in terms of centuries, not years. Our ancestors worked with a deep, almost intuitive understanding of the materials they pulled from the earth. They did not have our uniform, industrial strength components. Instead, they possessed a localized genius, a mastery of using what was available in ways that defied time itself. Consider the humble lime mortar, a simple mix of lime, sand, and water. Unlike modern cement, which is rigid and brittle, lime mortar remains slightly flexible. It allows a wall to breathe, to expand and contract with changes in temperature and humidity. Even more remarkably, it possesses a form of self-healing. When a tiny crack forms, moisture seeps in and dissolves a minuscule amount of the lime. This solution then travels into the crack and, upon contact with air, hardens into a new layer of stone, effectively sealing the wound. The structure heals itself. This principle of active, improving materials reaches its peak with Roman concrete. The Romans mixed their lime with a special ingredient, volcanic ash from the town of Pozzuoli. This ash, when combined with seawater, triggers a remarkable chemical reaction. Instead of eroding, the concrete forms rare, interlocking minerals that actually strengthen it over generations. A modern concrete seawall might crumble in 50 years, but a Roman pier, like the one in the harbor of Caesarea, has spent 2,000 years submerged in the Mediterranean, growing ever more resilient. This was not accidental. It was a profound knowledge of geology and chemistry, a recipe so effective it was lost for over a millennium. Builders did not simply place a structure on the land. They grew it from the landscape, creating a symbiotic relationship where the building and its environment supported one another. This foundational wisdom, prioritizing longevity and harmony over the speed of construction, forms the very bones of resilience. It makes you wonder what other secrets are hidden in the stones beneath our feet. That principle of using local materials was only the beginning of true symbiosis. The most resilient buildings are not just made from the land, they are shaped by it. Think of those Swiss chalets, their wide, overhanging eaves acting like a shield, protecting the wooden walls from driving rain and the summer sun. The steep angle of the roof is a direct response to the weight of winter snow, encouraging it to slide off before it can accumulate and crush the structure. Every single line of the building is a conversation with the local climate. This dialogue extends far beyond the mountains. In the deserts of the Middle East, ancient homes were built with wind towers, tall, chimney-like structures that captured even the faintest breeze and funneled it down into the living spaces, creating a natural and effective air conditioning system centuries before electricity. The thick, mud brick walls, sometimes several feet thick, served as a thermal battery, absorbing the intense heat of the day and slowly releasing the stored coolness throughout the night. Conversely, in regions prone to monsoons like parts of Southeast Asia, traditional stilt houses are raised high above the ground. This design allows seasonal floodwaters to flow freely underneath, leaving the living area dry and secure. The building does not resist the water, it accommodates it. This is the essence of symbiosis, a design philosophy that asks not how to conquer a force of nature, but how to live with it, how to let it pass through or around the structure with minimal harm. It is architecture as a form of respectful partnership. This deep, intuitive understanding of place informed every decision, from the orientation of a window to catch a prevailing breeze to the very shape of the roof. And it is this intelligent design, born from observing the world, that we will explore next. This respectful partnership with the environment gave rise to structures of breathtaking intelligence. Look up at the ribbed vaults and flying buttresses of a Gothic cathedral. These were not merely decorative flourishes, they were a revolutionary structural system. The pointed arch, unlike a rounded Roman arch, channels the immense weight of the stone ceiling more directly downward. The flying buttress then acts as a graceful brace, catching the outward thrust from the vaults and transferring it away from the walls, allowing those walls to be filled with vast, luminous stained glass. It is a skeleton of stone that turns crushing weight into soaring light. This mastery of geometry is a universal language in traditional building. The humble arch, the simple dome, these curved shapes are naturally strong because they distribute force along their entire curve, avoiding the stress concentrations that cause right angles to fail. Builders discovered that nature favors curves, and they encoded this wisdom into every bridge, every temple, every home. Nowhere is this more elegantly demonstrated than in a Japanese pagoda. These slender towers, some over 5 stories tall, have weathered earthquakes for centuries. Their secret lies in a central pillar that does not actually support the building. Instead, it acts like a giant pendulum. Each roof is built as an independent box stacked loosely on the one below. When the ground shakes, these stacked boxes sway in opposite directions, canceling out the energy. The central pillar swings, absorbing the remaining force, preventing the tower from snapping. It is a seismic dampener carved from wood, a concept so advanced we still study it today. These designs did not spring from a single brilliant mind, but from generations of observation, failure, and refinement. When a design worked, when it allowed a community to survive a storm or a quake, that knowledge was preserved and passed down, becoming an unspoken code for safety. This accumulated wisdom resulted in a built-in safety margin, a passive resilience that required no power, no maintenance, and no human intervention to perform its life-saving role. That forgiving design philosophy is the heart of a third, crucial principle, the art of building in a margin for error. Think of a traditional timber-framed house during an earthquake. Instead of being a rigid, nailed-together box that fights the shaking until it shatters, its joints are designed to flex. The wooden beams and posts are connected with intricate, interlocking joinery, sometimes held together only by their own clever geometry and gravity. This allows the entire structure to sway and rock, absorbing the earthquake's violent energy like a tree bending in a storm. It moves with the disaster, rather than standing against it in a battle it is bound to lose. This is passive resilience, a system that works without any power source or human intervention, relying solely on intelligent design to dissipate destructive forces. This approach is layered with redundancy. A traditional building rarely relies on a single critical point of support. Instead of one load-bearing wall, there might be several. A roof structure is often an intricate web of beams and rafters, where the failure of one element does not mean the collapse of the whole. Builders would intentionally oversize structural members, using a beam far stronger than strictly necessary. This provided a generous safety margin for unforeseen stresses, for the 1-in-1,000-year storm or the gradual settling of the earth over a century. You can see this wisdom in the very shape of a stone wall, often thicker at its base and gracefully tapering as it rises. This form naturally counteracts the immense forces of gravity and wind pressure, a built-in understanding of physics. In many Japanese and Chinese structures, the heavy tile roof is essentially an independent structure, sitting on top of the walls but not locked rigidly to them. When the ground moves, the roof can shift and slide slightly, a dance that prevents the entire building from being torn apart. The goal was never to remain perfectly untouched by disaster, but to degrade gracefully. A building might crack, it might sway alarmingly, but it would not pancake into a pile of rubble. It would give warnings, it would absorb the blow, and it would often remain standing, ready to be repaired. How does this margin for error create such enduring structures? It acknowledges a simple truth that the world is unpredictable. By designing for flexibility and extra strength, traditional builders created architectures that could endure the unexpected, a stark contrast to the brittle failure we sometimes see in modern constructions. This margin for error, this philosophy of graceful degradation, finds perhaps its ultimate expression in a building that seems to defy physics itself. In the heart of Rome stands the Pantheon, its massive, unsupported dome a silent challenge to nearly 2,000 years of gravity. To stand beneath that dome is to witness a miracle of engineering, a space so vast and open it feels more like the sky than a roof. The secret to its immortality lies in a profound, almost artistic understanding of material and form. The Romans did not simply build a dome, they sculpted it with intelligence. As the dome curves upward, the concrete itself changes. At the heavy base, the mix is packed with dense basalt stone, but as the walls climb, the aggregate becomes lighter, shifting to porous pumice near the very top. This genius move dramatically reduced the weight and the crushing stress on the lower walls, a calculated lightening of the load. And then there is the oculus, the great open eye at the center of the dome. It is not just a source of breathtaking light, it functions as a masterstroke of structural engineering. The continuous ring of the oculus acts as a perfect compression ring, distributing the immense forces evenly and stabilizing the entire vast shell. This is why, despite being the world's largest unreinforced concrete dome, it has shrugged off earthquakes and the slow decay of centuries. The Pantheon does not fight the forces acting upon it, it guides them, channels them in an elegant dance of compression. Its survival is a testament to a culture that thought not in decades, but in millennia. What other secrets are still locked within its ancient concrete, waiting for our science to uncover? This Roman mastery of standing firm against the slow grind of time leads us to a different kind of challenge, the sudden, violent shock of the earth itself moving. While the Pantheon stands as a monolithic triumph over gravity, another ancient structure survives through a philosophy of graceful movement. A 5-story Japanese pagoda does not resist an earthquake, it dances with it. In video footage from major tremors, these slender wooden towers sway with an almost rhythmic grace, their curved roofs flowing like waves. This is not a sign of impending collapse, but the precise operation of one of the most sophisticated seismic dampening systems ever conceived. The genius is in its deceptive simplicity. Each level of the pagoda is essentially an independent box stacked upon the one below. They are not nailed or bolted rigidly together. Instead, they are connected by complex, interlocking wooden joints that allow each story to slide and rock, almost floating on the one beneath it. This design absorbs and disperses the earthquake's energy horizontally, preventing it from traveling up the structure with destructive force. At the heart of this dance is the Shinbashira, a massive central pillar that runs up through the center of the pagoda. It is the most surprising element of all because it does not actually hold the building up. In fact, it often hangs suspended from the apex, just barely touching the ground. During a quake, this pillar acts as a giant, stationary pendulum. As the flexible stories sway around it, the pillar's inertia counteracts their movement, steadying the entire tower and preventing it from whipping back and forth uncontrollably. It is a system perfected over 1,400 years of living in one of the most seismically active regions on Earth. The heavy ceramic roof tiles add a final masterstroke, acting as a stabilizing weight, much like a dancer uses their center of gravity to maintain balance during a complex spin. The result is a breathtakingly effective form of passive resilience. Not a single traditional wooden pagoda in Japan has ever collapsed from an earthquake in recorded history. This is architecture that has learned from nature itself, mimicking the way a tall, flexible tree bends and sways in a storm, its roots and trunk working in harmony to dissipate the wind's energy. It is a dynamic conversation with the Earth's power, a conversation we are only now learning to have with our own modern buildings. This intimate knowledge of materials was not locked away in textbooks, but passed from hand to hand through generations of artisans. Step onto the grounds of a medieval cathedral under construction, a chaotic symphony of purpose without a single paper blueprint. The master mason did not work from a detailed drawing, but from a set of precise geometric rules held in memory, a living library of proportions and relationships passed down through the guild. His most vital tool was not his chisel, but his accumulated experience, the tacit knowledge of how a specific type of limestone felt when struck just right, or the exact consistency of mortar needed for a particular joint. This was a knowledge of the hand and the eye, a deep, almost spiritual respect for the materials themselves. A carpenter did not simply cut a beam to length. He understood how that specific tree had grown, how the wood would season over the coming year, and how it would subtly warp and settle over the next 50. This foresight was built directly into the structure. A wooden joint was not merely a connection, it was a work of artisanal engineering, carved to interlock with such precision that the connection would often grow tighter, stronger, under the very loads it was meant to bear. Each component, from the largest foundation stone to the smallest peg, was made with an eye toward its long-term performance and its role within the entire system. Unlike our modern world of standardized, interchangeable parts, every piece in a traditional building was unique, tailored by a skilled craftsperson to fit a specific place. The result was not just a building, but a cohesive, hand-fitted unit where every element supported the others. This level of care is a form of resilience in itself. A building constructed this way can be maintained, understood, and repaired by future generations using similar skills and local materials. It creates a legacy of stewardship. The stark question then becomes, in our age of rapid construction and disposable components, what happens to a building's chance for longevity when the knowledge of how to heal it is lost? This deep connection between builder and building inevitably extends to the community that gives it life. That intimate bond between craftsperson and material is only one part of a much larger support system. A building's true longevity often depends on a community that sees it not as a disposable asset, but as a living legacy. Take the wooden stave churches of Norway, dark and dragon-crowned silhouettes that have stood for over 800 years. Their survival is not a miracle of perfect engineering alone, but a testament to generations of local villagers who treated the structure as a sacred trust. Maintenance was not an inconvenient bill that arrived every few decades. It was a continuous ritual woven into the very fabric of community life. The annual re-thatching of a roof or the replastering of walls was not a chore, it was an event. Neighbors would gather, skills would be passed from elders to the young, and the building would be carefully inspected and healed. This created a living, breathing relationship between the inhabitants and their architecture. Small problems like a loose tile or a damp patch on a beam were spotted and fixed immediately by people who knew every inch of the structure. A catastrophic failure was almost impossible because decay was never allowed to gain a foothold. Most importantly, the knowledge of how to maintain the building was not stored in a manual, but embedded directly into the culture. A father would teach his son the exact angle to lay the thatch for the best runoff, or the specific mix of local clay and straw for the most durable plaster. This socio-cultural infrastructure is perhaps the most powerful, yet most fragile component of resilience. It ensures that the skills needed to preserve a building are never lost because they are practiced and celebrated by each new generation. This stands in stark contrast to our modern reality. How many of us know the people who built our homes or possess the skills to repair them with local materials? When a community's identity is tied to a place, that place is cared for with a devotion that no contract can mandate. This deep connection raises a vital question for preservation. What happens to a building that has outlived its original purpose? This is where the principle of adaptive use becomes essential for survival. A building's survival depends as much on its story as on its stones. Walk through the streets of Istanbul, and you can see this truth carved into the city's soul. Beneath the bustling modern city lie vast Roman cisterns, their cavernous spaces once holding the water supply for an empire. Centuries later, Ottoman architects saw not a forgotten ruin, but a foundation, building magnificent palaces directly above these subterranean wonders, using their sturdy arches for support. Above ground, the great church of Hagia Sophia, after standing for 1,000 years, was adapted into a mosque, its massive, robust structure easily accommodating the addition of minarets and new interior elements. Each transformation added a new layer of history and, crucially, a new reason for the community to maintain and strengthen the original fabric. These buildings survived not merely because their walls were thick, but because they remained deeply useful. Their inherent flexibility was a form of future-proofing. Thick masonry walls could be pierced for new windows or doorways. Vast, columned halls could be subdivided into smaller rooms. A structure designed as a fortress could become a palace, then a museum, its robust frame accepting each new identity without demanding demolition. This capacity for reinvention is a core aspect of resilience often overlooked. A building that can evolve with the needs of its inhabitants sidesteps the gravest threat of all, obsolescence. Unlike many modern structures built for a single, highly specialized purpose, traditional buildings were often inherently multi-purpose. Their spaces were generous and adaptable, defined by load-bearing walls and columns that created flexible zones rather than fixed, tiny rooms. This design philosophy begs a reflective question. How does designing for adaptability from the very beginning contribute to a building's potential lifespan? It ensures the structure remains a living, functioning part of the community, constantly cared for because it is constantly used. And this constant use, this battle against time, inevitably leads to a confrontation with a building's most persistent enemy, the relentless, patient power of water. Water is the most patient destroyer. It does not arrive with the violent shock of an earthquake, but with a slow, persistent seepage that rots wood, rusts metal, and crumbles stone from the inside out. The greatest test of longevity is not surviving a single disaster, but outlasting the endless, silent assault of rain, humidity, and groundwater. Traditional builders understood this enemy intimately, and they waged a brilliant, passive war against it using nothing more than shape, material, and physics. Look at the roof of a traditional Norwegian farmhouse. Its slopes so steep and wide they seem to embrace the sky. This design is not just for aesthetics, it is a highly effective moisture management system. The sharp pitch ensures snow and rain slide off quickly, while the massive overhang, sometimes extending several feet from the wall, acts as a permanent umbrella. It throws water a safe distance from the foundation, creating a dry moat around the building's base. The walls themselves are raised on a plinth of stone or packed earth, lifting the vulnerable wooden structure away from ground moisture and splashing rain. This is defense in depth, a layered strategy that stops water long before it can do harm. But the real genius lies in what happens when moisture does inevitably find a way in. Unlike modern buildings wrapped in impermeable plastic barriers, traditional walls were designed to breathe. They were built with porous, capillary active materials like lime plaster and certain types of mortar. If moisture penetrated the surface, these materials would wick it inward and then allow it to evaporate back out, effectively ventilating the wall from within. The structure could dry itself out, preventing the trapped dampness that leads to mold, frost damage, and structural decay. This principle of breathability was applied with remarkable specificity across different climates. In the humid tropics, homes were elevated on stilts not just for floods, but to allow air to circulate freely underneath, carrying away moisture and keeping the floorboards dry. In Japan, the ancient technique of Shou-Sugi-Ban involved charring the surface of cedar planks. This carbonized layer was not just visually striking, it was incredibly resistant to rot, insects, and fire, creating a durable shield against the elements without any synthetic chemicals. These strategies reveal a profound understanding that you cannot always prevent water from arriving, but you can control how it leaves. Modern waterproofing often creates a sealed environment where any breach leads to trapped moisture and rapid deterioration. Traditional methods, by contrast, created resilient, breathing skins that managed moisture over the long term. This mastery of keeping a building dry is intrinsically linked to another critical function, the regulation of temperature. How does a structure stay comfortable through blistering summers and freezing winters without any mechanical aid? The answer lies in treating the building itself as a thermal battery. That same mastery of moisture control reveals another profound secret: the building as a living thermal battery. Step inside a thick-walled adobe house on a blistering desert afternoon. The air is surprisingly cool, a stark contrast to the oven-like heat outside. This is not magic, it is physics in action. Materials like adobe, stone, and rammed earth possess high thermal mass. They are slow to heat up and equally slow to cool down. Throughout the day, the sun beats on the walls, but the heat penetrates only a few inches, taking hours to reach the interior. By the time the sun sets and the outside air turns cold, the walls have absorbed a vast amount of energy. They then begin to radiate that stored warmth back into the living space, maintaining a stable temperature through the night. The building is not just a shelter, it is a thermal flywheel, smoothing out the violent peaks and valleys of daily temperature swings. This passive climate control is engineered into the very form of the structure. In cold northern climates, traditional homes feature small, strategically placed windows facing the south to capture the low winter sun, turning the interior into a sun trap. The massive hearth, often built into a central stone chimney, would absorb heat from the fire and continue to radiate it long after the flames died down. Conversely, in hot, arid regions, buildings are often arranged around a central courtyard. This open space acts as a climate machine. The sun heats the air in the courtyard, causing it to rise and draw cooler air from the shaded rooms surrounding it, creating a continuous, gentle breeze. Wind towers capture even the highest breezes, funneling them down into the living quarters. This passive system does more than just keep people comfortable. It is a fundamental guardian of the building's structural integrity. Modern buildings, with their thin walls and reliance on air conditioning, undergo constant, stressful expansion and contraction as temperatures fluctuate dramatically between day and night. This thermal flexing fatigues materials, leading to cracks in drywall and failures in seals. A traditional building with high thermal mass experiences almost none of this stress. Its temperature remains remarkably constant, preventing the micro-damage that accumulates over decades into major decay. The structure is not fighting its environment, it is in a state of equilibrium with it. This inherent stability is a quiet, relentless contributor to longevity, proving that comfort and resilience are two sides of the same coin. That silver-gray patina on ancient wood is not a sign of neglect, but a badge of honor. Many traditional cultures built with a philosophy that saw beauty and strength in the natural process of aging. In Japan, this is known as Wabi-Sabi, a worldview that finds profound beauty in imperfection, impermanence, and the honest marks left by time. This was not just an aesthetic choice, it was a fundamental principle of resilience. Builders selected materials specifically for how they would weather. Copper was chosen not despite the fact it would turn green with verdigris, but because that protective layer would shield the metal beneath for centuries. Wood was left untreated to silver in the sun, a process that actually hardened its surface against the elements. This acceptance of change shaped the entire approach to maintenance. The goal was never to return a building to its original, as new condition. It was about preservation, about gently steering the structure through time. A crack in a lime plaster wall was not a catastrophe to be hidden. It was an opportunity for a repair that would become part of the building's story, a visible seam of history where one generation's care met another's need. This mindset completely alters the relationship between people and their structures. When you expect a building to change, to settle, to develop a character of its own, you are less likely to subject it to brutal, destructive renovations in the name of modernization. You care for it with a lighter touch, understanding that each repair adds to its narrative rather than detracting from some impossible ideal of perfection. This stands in stark contrast to our modern obsession with flawless, sterile surfaces that show every scratch and stain as a failure. A building that must remain forever new is a building destined for the landfill the moment it shows its age. But a structure allowed to age gracefully, to accumulate the gentle scars of time, earns a kind of reverence that guarantees its care for generations. How does our pursuit of perfection actually make our buildings more fragile? This philosophical acceptance of change is the final, crucial preparation for the ultimate test, a direct encounter with disaster. A modern concrete building can fail in a single, terrifying instant. Its rigid frame, designed to resist movement, meets an earthquake's force with brittle defiance until a critical column snaps. Then one floor collapses onto the one below, triggering a catastrophic chain reaction that leaves little but rubble. Now, watch a traditional timber-framed house during that same tremor. It groans and sways, its joints creaking loudly. The entire structure may lean precariously, and large cracks might snake up its plaster walls, but it rarely collapses. This dramatic difference lies in a deliberate design philosophy, one that embraces controlled damage over brittle perfection. Traditional structures are often non-ductile in the modern engineering sense, meaning they are not made of steel designed to stretch. Yet they possess a profound, inherent ductility through their very assembly. The secret is in the connections. A traditional timber frame uses joints that are not rigidly fixed. Mortars and tenon joints, dovetails, and other intricate woodworking connections allow beams to slide, rock, and twist within their sockets. These are essentially friction connections, absorbing the earthquake's energy by converting it into movement and heat. The building dances with the disaster, its components deforming significantly without completely losing their ability to bear weight. A masonry wall, too, can fail gracefully. While modern, rigid concrete might shatter, traditional brick or stonework with soft lime mortar can develop large, zigzagging cracks. The wall deforms, but it often remains standing, held together by the friction between the stones and the flexible mortar that acts like a cushion. This is a fundamentally different safety philosophy. It does not aim for the impossible goal of a building remaining perfectly untouched by an extreme event. Instead, it designs for a graceful degradation. The goal is to ensure that even when the structure is pushed far beyond its normal limits, it fails in a slow, predictable way that gives occupants precious time to escape and leaves a building that can often be repaired. Why is this often safer than absolute rigidity? Because nature's forces are unpredictable. Designing for a specific, theoretical maximum load is a gamble. But designing a system that can absorb a wide range of shocks by flexing and yielding is a surer bet on survival. This acceptance of controlled damage is only possible when the building's underlying systems are simple and understandable. A complex, highly specialized system is difficult to fix after it breaks, but a structure built with basic principles of friction and gravity can be repaired by anyone with the traditional knowledge using local materials. This repairability is the final, vital layer of resilience, turning a near disaster into a story of survival and renewal. A broken tile on a roof is not a crisis when the same clay lies in the riverbank just beyond the village. This is the profound strength of repairability, a principle woven into the very fabric of traditional architecture. After a storm, a community does not need to wait for a shipment of specialized materials from a factory on the other side of the world. They can gather local stone, cut timber from a managed forest, and mix mortar from lime and sand found nearby. The building and its environment are part of a single, sustainable cycle. If a wooden beam rots, a new one can be hewn to fit using the same tools and knowledge that built the original structure centuries before. This stands in stark contrast to a modern high-rise, which might depend on a specific type of custom-fabricated steel bracket or a unique glass panel. If that component is no longer made, or if the company that produced it goes out of business, a simple repair can become an impossible, costly puzzle. The knowledge required for these traditional repairs was not locked away in a corporate database. It was held locally, passed down from master to apprentice, from elder to child. A community carpenter knew the exact grain of the local pine, and a mason understood the peculiarities of the regional limestone. This meant that damage, whether from a sudden disaster or the slow creep of time, could be addressed immediately by people who understood the building intimately. A small crack was fixed before it could let in water and rot a wall. A loose stone was reset before it could compromise an arch. This constant, low-level maintenance prevented minor issues from escalating into catastrophic failures. It is a system that builds in resilience not just through design, but through an entire ecosystem of care and knowledge. Our modern reliance on complex, globalized supply chains creates a hidden vulnerability. What happens to a building when the only person who understands its complex systems retires, or when a critical part must be shipped across an ocean? A structure that cannot be easily healed by its own community is a structure living on borrowed time. This localized cycle of repair ensures a building's story is not one of eventual disposal, but of continuous renewal. A building's true resilience is measured not just by how it stands, but by how it begins and how it ends. Every traditional structure is part of a quiet, continuous cycle, one that starts and finishes in the earth itself. The stones are quarried from a nearby hillside, the timber felled from a local forest, the clay dug from a riverbank. The energy required to gather these materials is almost negligible, especially when compared to the industrial furnace needed to produce steel or the immense heat required for Portland cement. This is the principle of low embodied energy, the total amount of energy consumed by a material throughout its life, from extraction to disposal. For a traditional building, that number is astonishingly small. The construction site itself is a scene of human-scale effort, powered by muscle and simple tools rather than roaring diesel machinery. The process is slow, deliberate, and deeply connected to the rhythms of the land. But the cycle's true elegance is revealed at the end. When a traditional building finally reaches the conclusion of its long life, it does not become a toxic burden. A rammed earth wall can be simply knocked down, moistened, and recompacted to form a new wall. Its materials are literally returned to the earth, leaving no permanent scar. Wooden beams can be salvaged for new construction, and stone blocks can be reused for generations. There is no waste, only a return to the source. This sustainable loop is far more than an environmental virtue. It is a profound source of systemic resilience. A building method that is not dependent on global supply chains, volatile fuel prices, or specialized factories is inherently robust. Imagine a community recovering from a major disaster. If their homes were built with local earth and timber, they can begin rebuilding almost immediately, using the skills and materials at hand. They are not waiting for a shipment of concrete or steel beams that may never arrive. The knowledge of how to build is as local and accessible as the materials themselves. This creates a society that is far less fragile, capable of adapting and enduring even when larger systems falter. The resilience of the individual structure is therefore inseparable from the resilience of the community and the sustainability of its resource base. In an age of climate uncertainty and potential resource scarcity, this ancient model of low-energy, locally attuned construction offers a powerful blueprint for a future where our buildings are not just strong, but truly rooted. The narrow, winding streets of an ancient Persian city are not a maze of random choices but a masterfully engineered climate system. Stepping into one of these shaded alleyways on a scorching summer day is like entering a different world where the air is noticeably cooler and still. This is bioclimatic design in its purest form, a deep and intuitive collaboration with the sun, the wind, and the very flow of water. The Hagia or wind tower is its most iconic instrument. It is not merely a decorative chimney but a sophisticated air handler. Its openings are strategically positioned to capture the slightest prevailing breeze from high above the ground, funneling it down a vertical shaft and into the heart of the home below. To accelerate this flow, the air is often directed over a pool of water or a moist surface, cooling it further through evaporation before it spills into the living quarters. Meanwhile, the hot, stale air inside is pushed out through other openings, creating a continuous, self-sustaining cycle of ventilation that requires no energy beyond the wind itself. The city's layout itself is a climate moderator. The streets are deliberately narrow and twisted, not for defense alone, but to create long stretches of deep shadow throughout the day, protecting pedestrians and building walls from the sun's direct glare. The buildings are packed closely together, their thick, mud brick walls sharing shade and reducing the overall surface area exposed to the heat. This is not a fight against the desert climate, but a brilliant dance with it. The same principle applies in reverse in colder northern latitudes. A traditional farmhouse in Europe will be meticulously oriented with its longest side and largest windows facing south, capitalizing on the low winter sun to passively heat the interior. Deciduous trees might be planted nearby. They provide shade in the summer when their leaves are full, but allow the precious sunlight to stream through in the winter when they are bare. Every single decision, from the angle of a roof to the placement of a window, was a calculated response to local conditions. This ecological intelligence did more than just keep people comfortable. It dramatically reduced the environmental stresses on the building itself. A structure that stays cooler in summer experiences less thermal expansion, and one that stays drier in a humid climate is less prone to rot and mold. By working in harmony with natural forces instead of constantly battling them, these buildings avoided the slow, degrading wear and tear that plagues so many modern structures. In an era of climate uncertainty and rising energy costs, this pre-industrial smart design feels more vital than ever. It represents a fundamental shift from consuming energy to achieve comfort, to using intelligent design to harvest comfort directly from the environment. The winding streets of that Persian city were a testament to a deep dialogue with the elements, but that conversation begins even earlier with the very ground beneath our feet. Perched on a rugged Italian hilltop, a medieval town seems to grow directly from the stone. Its location was no accident of beauty, but a calculated decision for survival. The survival of any structure begins with this first and most crucial question: where do we place it? Traditional builders possessed an almost innate understanding of the land itself, a science we now call geomorphology. They knew to avoid the fertile, inviting floodplains where rivers periodically reclaim their territory. They shied away from unstable slopes that could surrender to landslides after heavy rains. Instead, they sought out stable bedrock, a firm foundation that would not liquefy during an earthquake. This choice of site is the most fundamental layer of resilience, a non-structural defense that often proves more vital than the thickness of any wall. It is a form of preventative wisdom. A castle built on a commanding outcrop is naturally defensible, yes, but it is also high above the rising waters and situated on ground that remains firm when the earth trembles. They prioritized access to fresh springs and positioned settlements to catch the sun's warmth while utilizing natural gradients for drainage, ensuring rainwater would flow away from foundations. Today, we often see the tragic consequences of ignoring this ancient logic. Neighborhoods built on filled wetlands succumb to floods, and houses on unstable coastal cliffs tumble into the sea. These are modern disasters exacerbated by a decision made on a map long before the concrete was poured. How much inherent safety do we sacrifice when we prioritize a convenient location or a scenic vista over the long-term stability that our ancestors took for granted? A safe site provides the silent, stable stage upon which all other architectural innovations can perform. It is the unshakable base that allows a building to dance with the wind and endure the tremors of time. The true strength of a building lies not in its solid beams, but in the silent, shifting spaces between them. Within the dark eaves of a Chinese temple roof rests a masterpiece of wooden engineering, the dugong bracket. To the untrained eye, it is a complex puzzle of interlocking pieces, a sculptural marvel. But its beauty is purely functional. Each bracket is an assembly of wooden arms and blocks, carved to fit together with such precision that no nails or glue are needed. The genius of this system is how it manages force. The immense weight of the heavy ceramic tile roof does not bear down on a single point. Instead, the dugong catches this load and, like a set of wooden hands passing a heavy weight, distributes it outward across a network of columns below. As the weight settles, the wooden components compress, the joints growing tighter and stronger under the very pressure they are designed to bear. This is a connection that improves with age and stress, becoming more secure with each passing year and every heavy snowfall. This philosophy of flexible connection was universal. In the timber-framed barns of medieval Europe, massive oak beams were joined with intricate mortise and tenon joints. These connections were not rigid locks. They allowed the entire structure to breathe, to sway gently in the wind, and to settle into the ground over decades without cracking apart. In regions frequented by earthquakes, this principle was pushed even further. Joints were specifically designed with a calculated looseness, allowing beams to slide and rock during a tremor. This movement absorbs the earthquake's destructive energy, dissipating it as friction within the wooden joints instead of letting it build up to a shattering force. These sophisticated details were not the product of a single engineer's calculation. They emerged from generations of observation, from watching how trees move in a storm and understanding how wood behaves under stress. This accumulated wisdom created a language of connection that gave buildings a supple, almost living strength. The shift to modern nailed or welded connections represents a fundamental change in philosophy. A rigid metal fastener tries to hold two pieces perfectly still, creating a point of immense stress. When a force becomes too great, the wood around the nail can splinter or the weld can snap, leading to a sudden, catastrophic failure. The traditional joint, by contrast, is designed to move, to give way just enough to survive. It prioritizes the integrity of the whole structure over the absolute fixity of any single part. The intelligence hidden within a single dugong bracket is a perfect microcosm of the entire building's resilient soul. The soaring arches of a Gothic cathedral do more than lift the gaze toward heaven. They encode a hidden mathematical language. Across the world, from the intricate stonework of Hindu temples to the serene courtyards of Islamic mosques, traditional builders worked from a set of sacred geometric rules. These were not arbitrary choices. Dimensions were based on ratios like the golden section, a proportion famously found in the spiral of a nautilus shell and the branching of trees. This was seen as a divine blueprint, a way of connecting an earthly structure to the perfect order of the cosmos. A temple was a cosmological diagram made real in stone, and its stability was believed to be a reflection of that universal harmony. This symbolic dimension had a profoundly practical consequence. It enforced a rigorous discipline. A master mason did not design by whim. He followed precise canonical rules passed down through generations, a geometric recipe that, often through intuitive wisdom, resulted in forms that were inherently stable. The repeated use of the golden ratio, for instance, creates proportions that are naturally pleasing to the eye, but they also distribute structural loads in an exceptionally balanced way, preventing stress concentrations. This symbolic framework acted as a fail-safe for quality control. It ensured that building knowledge was transmitted with remarkable accuracy over centuries. A craftsman in one century, building a temple to the same divine principles as his ancestor 300 years prior, would replicate not just the appearance but the underlying sound geometry. The building's deep symbolic meaning fostered a powerful cultural imperative for its preservation. It was not merely a physical shelter, it was a vessel of spiritual meaning, a landmark of identity. To allow such a structure to fall into disrepair was to neglect a sacred trust, to break a link with the divine order itself. This raises a challenging question for our modern world. When a building is conceived primarily as a financial asset or a functional container, designed for a short lifespan with little symbolic weight, what incentive does a society have to maintain it for 500 years? The loss of sacred geometry may have cost us more than beauty. it may have weakened the very cultural will needed for true longevity. A fallen tower speaks more clearly than one still standing. For every ancient structure that has defied the centuries, countless others lie in ruins, and their broken stones hold a different kind of wisdom. The history of resilient architecture is not just a chronicle of success, but a story written in the ashes of failure. Each collapse, each destructive fire became a brutal but effective teacher, forcing communities to analyze what went wrong and adapt their methods. The slender minarets that swayed too violently in the wind taught later builders about the invisible forces of wind loading, leading to more stable profiles and reinforced bases. When entire cities built of wood were consumed by flames, the trauma gave birth to a new idea: the deliberate creation of fire breaks, open spaces that could starve a fire of fuel. In Japan, the repeated incineration of dense urban neighborhoods led to the establishment of hyochi, designated fire break areas that became permanent features of the urban landscape. This was not a top-down mandate from a distant authority, but a cultural response forged in the heat of disaster. Knowledge was codified into unwritten rules, then into formal building traditions. A thatched roof might be outlawed within city limits, replaced with clay tiles. A builder might be required to plaster the exterior of a wooden wall to slow the spread of flames. These were traditional building codes written not on paper, but in the collective memory of a people who had learned the hard way. This process of iterative learning, of building, failing, understanding, and rebuilding better, is the very engine that drove architectural resilience for millennia. It created a cumulative body of knowledge that was constantly tested and refined by real-world events. Our modern approach, with its complex computer models and standardized codes, risks losing this vital feedback loop. We can become so confident in our theoretical calculations that we forget to listen to the lessons of the past. How can we reincorporate this humble, learning-based approach where every failure, whether ancient or modern, is seen not as a final defeat, but as an essential step toward creating buildings that can truly endure? A gleaming skyscraper of steel and glass appears unshakable, a monument to modern engineering's quest for absolute strength. Yet compare its rigid frame to the weathered wooden skeleton of a centuries-old barn. The barn seems fragile by comparison, but it holds a different kind of power. It embodies a critical paradox: the distinction between pure strength and deep resilience. Modern design often focuses on achieving maximum performance under predicted conditions, using materials of incredible strength that behave in highly predictable ways. This creates a robust system, one designed to resist change perfectly within a narrow band of expectation. But when an unexpected force arrives, one that falls outside those precise calculations, the system has no give. A connection designed for ultimate strength can become a point of catastrophic, brittle failure. Traditional architecture, by contrast, rarely pursued maximum strength. Its goal was sufficient strength layered with forgiveness. It is a resilient system designed to absorb shocks, to degrade gracefully, and to be repaired with local means. Think of it as the difference between a mighty oak and a willow in a hurricane. The oak stands rigid against the wind until its trunk snaps. The willow bends, its branches whipping violently, and when the storm passes, it springs back, bruised but intact. The modern skyscraper is the oak, engineered for a specific wind speed. The ancient barn is the willow, designed for the storm it cannot predict. This resilience is built from redundancy, the use of multiple load-bearing elements so that if one fails, others can share the burden. It is found in the forgiving nature of its materials, like flexible wood and soft mortar that allow for movement without fracture. And it is rooted in repairability, a design that anticipates damage and makes fixing it a simple, localized task. In an age of increasing climate volatility, where the 100-year storm may now arrive every decade, this question becomes urgent. Are we building for a world we can perfectly model, or for the unpredictable world that actually exists? The metrics of success may need to shift from how much force a building can theoretically resist to how gracefully it can survive the forces we never saw coming. A silent crisis is unfolding within the very walls meant to be preserved. The greatest danger to a centuries-old building is rarely a single cataclysm, but a slow, well-intentioned death by modernization. Walk through any historic district and you will see the tragic signs. A beautiful stone house, standing strong for 300 years thanks to its breathable lime plaster, is suddenly covered in a hard, impermeable coat of cement-based render. To the untrained eye, it looks like a clean, modern improvement, but this new skin acts like a plastic bag, trapping moisture inside the walls. The ancient masonry, which for centuries had breathed, allowing dampness to evaporate harmlessly, now begins to rot from within. Trapped moisture freezes in winter, expanding and spalling the stone face. It encourages mold and relentlessly dissolves the soft, flexible mortar that was the building's original shock absorber. This single, misguided act can accelerate decay more in 20 years than natural weathering did in 200. The same tragedy occurs when original wooden windows, designed to be repaired and whose slight porosity allowed the building to breathe, are ripped out and replaced with sealed, double-glazed PVC units. The new windows may be more energy efficient on paper, but they create an airtight seal that disrupts the entire building's delicate moisture equilibrium, often causing condensation and rot in the surrounding frame that goes unseen until it is too late. This loss is compounded by an even more profound erosion, the disappearance of the artisans themselves. The master thatcher who knows the exact angle and thickness of reed needed for a roof to last 50 years, the lime plasterer who can mix a mortar with the perfect consistency and breathability for a particular type of stone, these keepers of a deep, tactile knowledge are retiring without successors. When the last person who knows how to properly maintain a traditional building is gone, that structure becomes a museum piece on life support, its fate tied to expensive, invasive interventions by specialists who may not fully understand the original system. The building still stands, but the living tradition of care that sustained it is broken. Preserving the physical shell is only half the battle. The true challenge is safeguarding the intangible knowledge that allows these structures to live and breathe. A new library in the desert stands cool and silent, its walls formed from the earth on which it sits. These are not simple mud bricks, but massive rammed earth walls, compressed with modern precision to achieve a density our ancestors could only dream of. Yet, integrated seamlessly into its broad roof are sleek photovoltaic panels, and embedded within its thick walls are tiny sensors that monitor temperature and humidity in real time. This building represents the most exciting frontier in architecture, a synthesis where ancient wisdom does not resist new technology, but embraces it. The goal is not to abandon modern innovation in a nostalgic retreat to the past, but to perform a careful integration, creating a hybrid approach that is greater than the sum of its parts. Engineers are now using supercomputers to model the intricate forces within a centuries-old dugong bracket. By simulating the complex interplay of its wooden arms, they can translate the principle of flexible, distributed load bearing into new designs for earthquake-resistant steel frames. The ancient joint teaches the algorithm, and the algorithm helps us build safer cities. Similarly, the challenge of insulating a historic stone building is being solved with new, highly breathable aerogel and wood fiber insulations. These advanced materials can be added to interior walls, dramatically improving energy efficiency without trapping moisture and causing the rot that impermeable foam would guarantee. This is the core of the new philosophy. It proves that traditional principles like passive thermal mass, redundancy, and breathability are not outdated concepts. They are essential, timeless ingredients for sustainability. The question is no longer whether we should use old ways or new tools, but how we can weave them together into a new architectural language. Can a smart building also be a breathing building? Can a sensor network help maintain the passive resilience of a thick wall? This synthesis points toward a future where durability is not a battle against nature, but an intelligent collaboration enhanced by the best of both worlds. A towering minaret of sun-baked mud rises from the Mali Desert, its surface etched with wooden beams that project like spines. This is the Great Mosque of Djenné, a structure rebuilt community by community for over 7 centuries. On the other side of the continent, the ancient high-rise city of Sana'a in Yemen presents a completely different silhouette, with its dizzying stone towers decorated in intricate white gypsum filigree. They could not look more different, one an organic form from the earth, the other a geometric marvel carved from mountain stone. Yet these two distant traditions speak the same silent language of survival. Both use massive walls of local material, whether rammed earth or stone, to act as a thermal battery, keeping interiors cool by day and warm by night. Both structures are designed with breathable skins, allowing moisture to pass through without causing damage. And both are sited with profound intelligence, the mosque on a raised platform above the floodplain, the Yemeni towers on stable, elevated ground. This is the stunning revelation when you scan the globe. From the floating reed islands of Lake Titicaca to the ice-defying sod roofs of Iceland, human ingenuity has arrived at the same answers to the same fundamental problems. The need to manage gravity led to arches and domes in both Roman and Mughal architecture. The threat of earthquakes inspired flexible timber frames in Japan and similarly jointed stonework in parts of the Himalayas. This is not a story of one culture copying another, but of parallel discovery. It is a powerful argument that these principles are not just cultural preferences, they are emergent properties of physics, materials, and human need. This universality gives us something incredibly valuable, a vast and time-tested library of solutions. When we understand that a building's ability to breathe is as important in a humid Scottish castle as it is in a dry adobe pueblo, we stop seeing these as isolated curiosities and start recognizing them as fundamental laws of durable construction. What does this shared heritage teach us? It tells us that the deepest wisdom of building is not owned by any single culture, but is a common human inheritance, waiting to be rediscovered and applied wherever we seek to create something that lasts.